Hi, I'm John Goldsmith, and this is a video in a series about learning language from first principles. And in this video, I'm going to be talking about finding chunks. I'm going to break this up into a couple of videos, but it's all part of the topic of finding chunks in natural language. Let me explain a little bit about what I mean by finding chunks. Here, we're talking about the problem of basically taking a long string of symbols and breaking them up into a sequence of units that are one or more symbols long. Basically, think of a book-length text in some language in a computer-readable form, or as a sequence of letters in some particular alphabet. And suppose we've eliminated the spaces, any kind of demarcation between words. So our challenge is to find what the words are in this particular corpus that we're looking at, this particular string of symbols. That's what I mean by finding chunks, finding pieces that are one or typically more than one symbol in length in such a way that the discovery of that set of chunks sheds light on how this particular corpus, this particular string of symbols was generated or created in the first place. I should say a little bit too about what I mean by first principles. I think that's a notion that'll only become clear as I proceed through this and other videos. But it's a term that I've borrowed from Kalelius Gurus. The idea here is that we want to think about the problem of learning language starting from scratch. And I don't mean, when I say starting from scratch, starting from knowing nothing. No, in fact, I'm starting with everything that I've learned about linguistics and machine learning and so forth. I have that knowledge, but I want to start again from the beginning. So we talk as if we hadn't built up our knowledge of English or any particular language. Again, you'll see more about what I mean by that as we proceed. There are three natural ways to start the problem of language learning from this sort of first principles point of view. Well, there are more than three, but there are three that come to mind very, very easily at this point. One of them has to do with probability, and we could build probabilistic models in which the probability of particular chunks that we're discovering are conditioned by neighboring chunks, either to the left or to the right. We'll talk about that, but that's not what I'm going to talk about today. The second question that we could consider, which is the one that we're going to consider right now, is the problem of discovering chunks. That is, to find pieces that are typically, on average, more than one symbol in length, such that the entire corpus can be viewed as a concatenation of these chunks. And then the third way in which we could proceed to learn structure about the system that we're studying is to learn categories. So we could learn categories into which either the symbols that we see or the chunks that we discover, we could consider assigning these to categories and seeing if these categories can help us better understand the character, the nature of the string of symbols that we're analyzing. I'm not going to talk about that here either. So both A and C, the consideration of neighbor dependencies, probabilistic dependencies between neighbors, and discovery of categories, both of those I'll consider in future videos, but not here. Here I'm going to focus on the problem of discovering chunks. So, chunking or word discovery. What's our gold standard? Okay, the gold standard means this, and it's a question that we raise in the context of evaluating how our work is going. In the context of computational linguistics, which this material all ultimately is computational linguistics, there's a very important principle that's been held sway in the computational linguistics community for 30 years. Which is that it's extremely important to keep a quantitative evaluation of how well your system is going at any particular time. There's more to be said about that, but if you're going to have a quantitative evaluation, one of the crucial characteristics is that you have to decide what the right answer is for the problem that you're trying to solve before you get going. You don't want to first write an algorithm, look at the output, and then decide whether that's correct or not, because you'll always modify your notion of what's correct based on what your algorithm has produced. It's just inevitable. It's part of being human. It's the Pygmalion effect. So in the case of word discovery, this is really not a difficult problem compared to most computational problems. We're going to look at a language. We'll look at English here. And I've decided that the gold standard, what counts as correct, is where there are spaces in the normal spelling of a corpus. I'm going to not worry about punctuation, periods, commas, exclamation points, and so forth. But the correct analysis will be the analysis that is in the corpus that we're looking at. If there are two words separated by a space, well, we want the system to discover that these two elements are distinct chunks. Again, you'll see that more clearly as we proceed. But what's crucial is that we have to have some conversation about what counts as the truth, what counts as the gold standard. And it is certainly the case that after we go back and look at how our algorithm does when it looks at English, we can have certain questions in our mind. So if we see a word like don't, for example, contracted form of do not, we could ask, should we be considering this one word or two? I'm going to make the executive decision that since there's no space in don't, the right answer for the analysis of don't is DON''T. Fine. Things to worry about, but in fact, the things that the questions that arise from contractions and so forth are really just a small part of the questions that we'll be interested in. Where is meaning in all this? Okay, well, this is an important point that's lurking in the background. We're going to try to discover words without any access to meaning. None, zero, zilch. Is that right? Is that wrong? Well, we'll learn something about the task of word learning if we approach it from the point of view of word learning without meaning. So let's just accept this as a premise we're starting with. Then we can draw some conclusions when we're all done. Minimum description length. This is going to be the heart of the approach that we're going to discuss. The work that I'm describing is, in my own intellectual biography, motivated by work by Michael Brent and Carl DeMarkin in the mid-1990s. Both Brent and DeMarkin were grad students in computer science at MIT in the mid-90s. They did work more or less independently. They didn't publish papers together. They both considered the ways in which this framework called minimum description length can make very interesting suggestions for the treatment of this problem of discovering words or chunks in natural language. I think it's fair to say that my work has been influenced more by Carl DeMarkin's work, but I certainly recommend that if you want to pursue this, you'll go back and look at the work both of Michael Brent and Carl DeMarkin. So, as I say, we're going to talk about minimum description length analysis and how this relates to Bayes' rule and a number of things. Okay, I'll come back to that. There are two problems of word discovery. One is relatively simple. One is much more difficult. It's the difficult one that we're interested in here today. So there's one problem which says that given a long string of symbols, perhaps the phonetic transcription of something of the piece of speech, and given our knowledge of the language from which it's drawn, cut that up into pieces, into the words. That's basically a problem that people who work in continuous speech recognition deal with all the time. We've got a continuous string, split it up into words. Okay, That's not the problem we're interested in here today. The problem that we're interested in is, given a very large corpus, reverse engineer it and figure out what the words are. With that, we should be able to go back and solve the first problem in any given case, given a corpus in which there are no spaces, put the spaces back in. That's the relatively easy problem, not easy in reality, but relatively easy. The hard problem is the one we're interested in, which is, given no knowledge of the language from which a very large corpus is drawn, reverse engineer it to figure out what the words are. That's what we're interested in. We're going to talk about probability, and the crucial point here is we're going to be talking about probability not in the context of uncertainty. It's going to be in the context of information theory, and this is something that is quite new for most linguists. We'll be talking about information theory. We'll be talking about measuring the complexity of a choice using probability theory to do that, and that'll be the crucial point. We're going to talk about structure and redundancy and the way in which these two terms actually refer to the same thing. Linguists refer to this thing as structure. In the context of information theory, it's typically referred to as redundancy. For linguists, it's what's interesting. Typically for information theory, redundancy, the point of discovering redundancy is you can get rid of it. Okay, so this makes it very surprising to hear that redundancy and structure are two sides of the same coin. They are, in a sense, the same thing, but I will explain just why that is. And of course, it leads to certain questions about how we can facilitate communication between people who know about information theory on the one hand and linguists on the other. And we'll be talking then about encoding and compression, which are really at the heart of information theory. So there we are. Okay, let's get started then. So let's look at Bayes' rule and the path that takes us from Bayes' rule to MDL. And I'll just say MDL from now on for minimum description length, which is a name given to an approach developed by, and the name was given by Jorma Rissanen, who's a Finnish-American statistician who spent most of his career at IBM. Okay, so we start with Bayes' rule. And Bayes' rule basically says that the probability of B given A is equal to the probability of A given B times the probability of B divided by the probability of A. Okay, so to understand that, you need to understand a bit about what conditional probability means. What does it mean to say the probability of B given A? And then what you see is that Bayes' rule is a way of reversing that condition. So if we go from the probability of A given B to the probability of B given A. That's what it's about. Okay, in order to understand that, well, it's actually very easy. It's actually just an algorithm. It's just an algebraic identity. So let's just walk through those steps. So the first step is to give the definition of the probability of A given B. And that's defined as the probability of A and B divided by the probability of B, capital B, that should be. Okay. The probability of B given A is defined as the probability of A and B divided by the probability of A. With there, I've used the fact that that the probability of A and B is the same as the probability of B and A. So, given those two definitions of probability of A given B and probability of B given A, we can just multiply by the denominator in each side. So on the left, we get probability of A and B is equal to the probability of A given B times probability of B. And on the right, which we're doing simultaneously, we've got the probability of A and B is equal to the probability of B given A and probability of A. Two things equal to the same thing or equal to each other, so we combine to give us that third step. Probability of A given B times probability of B is equal to the probability of B given A times the probability of A. We're almost there. Now we just divide both sides by the probability of A, and we're done. So we've got the probability of B given A is the reverse conditioned probability of A given B times the probability of B divided by the probability of A. And we're done. Okay? That's Bayes' rule. It's where it comes from. It's just a very simple algebraic manipulation of the definition of conditional probability. Okay, turn to the next slide. And here something kind of cool happens. So we're no longer going to just say A and B. We're going to be a little bit more concrete about it. We're going to talk about the probability of a hypothesis and the probability of data. Those are two treacherous notions, which we will be talking a lot about, but just take for now the thought that we could assign a probability to a hypothesis and that we can assign a probability to a set of data. Yes. Just accept that for the moment. And if we do, then we see that Bayes' rule tells us what I've written here. The probability of a hypothesis given a set of data D, we call the hypothesis H, okay? And of course, if we could calculate that, that would be terrific, right? We'd like to know, given a set of data, what's the probability of this hypothesis? Wouldn't that be great to have a system that could grind out the answer to that? We go from data to somehow knowledge of hypotheses. Okay, Bayes' rule tells us that's the same thing as it's mathematically equivalent to what you see on the right, the probability of the data given the hypothesis times the probability of the hypothesis divided by the probability of the data. Okay, has this helped us? Well, the notion of the probability of the data is obscure. What does it mean? You might say, well, before the data was created by somebody, its probability was very small, but after it was created, its probability was 1 or something like that. Well, that's really not very helpful. What we're going to do is punt or make an end run or get around it in any event. What we're going to do is this. We're going to modify the expression that we care about. And instead of calculating the probability as such, we're going to say, well, you know, what I care most about is which is the hypothesis that has the highest probability given the data. I don't care that much about what the probability is, but what I care is basically ranking different hypotheses. That's what science is about, after all, you might say. And in that case, we can say the following. Argmax, as we consider all hypotheses, of the probability of the hypothesis given the data. Well, before I get to the equal sign, I should say about what this argmax, as we look over all the different hypotheses. What is this argmax? Well, argmax is a notion that people use in machine learning all the time, and it basically says, let's consider all of the H's, possible hypotheses, and find out which of them assigns the highest probability. Well, probability because that's what follows. This is basically like a function that says, given a set, I'm going to find the element that has the largest value. And so we're generating this set of values, one for each hypothesis. And so argmax says, okay, give me the hypothesis that's associated with the highest value. Even though I don't particularly care what the value is, I want to know which hypothesis is associated with the highest value. And that's what argmax means. Okay, so on the left we have argmax as we iterate over all the hypotheses. The probability of the hypothesis given the data. That's the same thing as argmax over, and then what follows, that's just another way of writing the probability of H given D by Bayes' rule. Now, however, we can modify that. We can throw out the denominator, which was that problematic probability of the data. Why? Because we don't really know what that means, the probability of the data. but it's going to be constant. It's fixed for all the different hypotheses. And so it's only going to change the absolute value. It's not going to change the relative values. And therefore, the value on the right, argmax, we can just say it's the argmax over the product of the probability of the data given the hypothesis times the probability of the hypothesis. And that's a good step, and it's a big step. Okay, we proceed. And so now we're going to use a notation. It's, again, very standard. I'm going to say h hat. So this is just a way of saying the hypothesis that I care about. It's a particular hypothesis, and I care about it, and the reason is what I explained, that it's the best hypothesis that we can, as far as our calculations are concerned, given the data. Okay, so it's equal to argmax over h of the probability of the data given the hypothesis times the probability of the hypothesis. Okay, next thing that we can do is, okay, here I'm going to take a mathematical interlude for a moment. Let me just take a quick break here and present a slightly different slide. A quick interlude then, a little bit about distributions and logarithms. So a distribution is really important. If you want to talk about a probability, it has to be in connection with a particular distribution. And what is a distribution? For our purposes, we'll say that a distribution is a list of numbers, none of which are negative, they have to be 0 or positive. None of them are negative, and they sum to 1. And if the set that we're talking about, where each element of the set gets one of these numbers, if that set is fairly large, then obviously those probabilities, the individual probabilities, these numbers that add up to 1, each of them has to be fairly small, because you're divvying up, so to speak, that 1.0 over each of them. And in most cases that we care about, in fact, it's an infinite set. And so the numbers have to get real small, as you can imagine, since they have to add up to 1 in the limit. Okay, so that's the first fact. Here's just an example of a particular distribution. This is not a probability distribution, it's a frequency distribution. But as far as that's concerned, it's a distribution nonetheless. So here's an example of, I just counted the length of words in a particular corpus. Some words were 1 letter long, 10 letters long, all the way down to 18 letters long. That was the longest word. And I counted up how many there were, and then I divided by the total number. And so you see, we've got these numbers here in essentially the third column, going from 0.0834 all the way down to, well, at this point it looks like 0.0000, and then there's some number off to the right. These numbers all add up to 1, so it's a distribution. We could add other zeros after it, 19, 20, and so forth. They get zeros. As you can see, 17 got a 0 as well. Okay, so typically the probability associated with each whatever we're talking about with each of them is typically very small. And so it's much more convenient for us to talk about the logarithm of the number, and in particular, not just the logarithm, but -1 times the logarithm. And so I'm going to use a word, plog, which basically is short for a positive log. So logarithms of numbers between 0 and 1 are always negative. The log of 1 is 0, and the log of something larger than 1 is positive. But a number between 0 and 1, its log is negative. And nobody likes working with negative numbers when you can avoid it. So instead of using them, we multiply by -1, and we've got then the positive log, or plog. And so here you see at this table, you can see, I should say in addition, we're using base 2 logs here, so that if we've got 0.5, the plog of that is 1. The base 2 log of a half is -1, and that's because it's 1 over 2. The number half is 1 over 2. 2 is 2 to the 1. And so the log of 2 is 1, and the log of 1/2 is minus 1 times that. So the log of a half is minus 1, and therefore the log is 1. And so for exactly the same reason, the log of a quarter, 0.25, is 2. The log of an eighth, 0.28, is 3. The log of a 16th is 4. Each time we divide by 2, we increase the log by 1. The log of basically 1 over 1,000, really 1 over 1,024. The log of that is 10. The log of the log of 1 over a million is almost 20, because as you can see, the log of 1,000 is almost 10, and so the log of a million, which is 1,000 squared, is almost 20. So logs get larger much, much, much slower than the numbers themselves get smaller. Okay, so logs are a really fine way to describe small numbers, but it's sort of upside down compared to the way we usually think about things. The bigger a log is, the smaller the probability. That's what you want to bear in mind. It's a little bit like markedness, if you're a linguist who thinks about markedness, if you think that marked things are less likely. So, in short, the log of a number is minus 1 times the base 2 log of the number, which is exactly the same thing as saying it's the base 2 log of the reciprocal of the number. And so there's a graph. It could be helpful. The probability, our x, is represented on the x-axis, and the log is represented on the y-axis. So the smaller the x, the larger the log is. And there you are. Okay, here's an example. I calculated the log for each phoneme in an English corpus. And so here you've got the word stations with the phonemes here, S, T, A, sh, and so forth. And I've drawn a rectangle whose height is the log in each case. So you can see that a phoneme like schwa, which has a high frequency in English, has a log that's about 3.5. Sh is a much less frequent phoneme in English, and it's got a log that's up around 7. So there's an example of what logs are doing. And now we can get back to Bayes' rule and minimum description length, MDL, and use the concept of log. So here we are back again at this same slide. We were talking about Bayes' rule, using Bayes' rule when we talk about a hypothesis, H, and a set of data, D. And so we had that first line, we talked about that already. H hat is equal to argmax as we consider all of the different hypotheses of the data given, considering the expression which is the product of the probability of the data given the hypothesis times the probability of the hypothesis. Now I'm going to take the log of that product. So the product is the P of D given H times P of H. I take the log of that. So the log of the product is equal to the sum of the logs. So we have the log of P plus the log of P of D plus the log of P. And now I multiply that by minus 1 because both of those were negative numbers. And so that's the log of D plus the log of D given the hypothesis H plus the log of H. But because I've multiplied by minus 1, I no longer am looking for the largest value, but rather the smallest value. So it's argmin, considering all of the hypotheses in my universe. We look for the smallest value that sums the log of D given H and the log of H. Or as I wrote there, choose the hypothesis H such that its length, I'm going to tell you why length comes in here, its length plus its compression of the data is minimized. And of course I have to explain that too. What does this mean, the compression of the data? Okay, that's the concepts that lie behind those terms. But then the big box to bear in mind then is the description length of a set of data D given hypothesis H is the log of the H plus the plug with hypothesis H of the data. Choose the H that minimizes the description length of this data. That's what MDL is telling us, and that's what we're going to use, and we're going to try to use that in order to find words in a long corpus. So here we are back again at this same slide. We were talking about Bayes' rule, using Bayes' rule when we talk about a hypothesis H and a set of data D. And so we had that first line, we talked about that already. H hat is equal to argmax as we consider all of the different hypotheses of the data, considering the expression which is the product of the probability of the data given the hypothesis times the probability of the hypothesis. Now I'm going to take the log of that product. So the product is the P of D given H times P of H. I take the log of that. So the log of the product is equal to the sum of the logs. So we have the log of P plus the log of P of D plus the log of P. And now I multiply that by -1 because both of those were negative numbers. And so that's the plug of D plus the plug of D given the hypothesis H plus the plug of H. But because I've multiplied by -1, I no longer am looking for the largest value, but rather the smallest value. So it's argmin, considering all of the hypotheses in my universe. We look for the smallest value that sums the plug of D given H and the plug of H. Or as I wrote there, choose the hypothesis H such that its length, I'm going to tell you why length comes in here, its length plus its compression of the data is minimized. And of course I have to explain that too. What does this mean, the compression of the data? Okay, that's the concepts that lie behind those terms. But then the big box to bear in mind then is the description length of a set of data D given hypothesis H is the plug of the H plus the plug with hypothesis H of the data. Choose the H that minimizes the description length of this data. That's what MDL is telling us, and that's what we're going to use, and we're going to try to use that in order to find words in a long corpus. Well, now we get to the heart of the matter, and I'm going to jump right in. There are a few other things I could say in a preliminary sort of way, but I think I'll go with a little bit more concrete, and when I'm done with that, we'll sort of go back to some of the ideas that I'm glossing over a tiny little bit. Okay, so what we're doing now is talking about how to create a grammar for a word breaker. And so what we're going to do is keep our eyes on three things: an alphabet, capital A corpus, capital C, and a lexicon, capital L. So the corpus is given to us, and I think of it as a string that's a million characters long, let's say. There are no spaces in it. It's in some alphabet, and it's easy to, we don't even have to decide the alphabet in advance. We just run through it and just count up all the different letters that are there. And I'll just assume it's a computer-readable string of some sort. And as I say, there's no indication of word breaks or anything. That's our goal, to figure out what the words are. Okay. We want to be able to talk about the length of a grammar, and we want to talk about the length or the compressed length of the corpus. Well, the grammar, let's talk about the grammar for a moment. The grammar just consists of two things: a rule, I'll call it rule 1, there isn't a rule 2, and the lexicon that it deals with. All right. So the length of the grammar is the length of one rule plus the length of the lexicon, and we'll be measuring that length. So I have listed the main points here, and I'm oversimplifying on just a couple of them, and I've indicated those oversimplifications with a dagger. Okay, first point. A is our alphabet. That's simple enough. And then A plus is the name that we give to all the finite strings that can be made from A. That's just standard. You know, I could say A star, but A star includes the null string, and we're not interested in the null string. So we used A plus. Then we've got the lexicon L, and the lexicon is a subset of A plus. It's just some selection of finite strings that come from the alphabet. And I'll also assume that the alphabet is a subset of the lexicon. So if the alphabet is the letters A through Z will always be members of the lexicon. Then there's a rule, I called it rule 1, and it takes the form S goes to W star, where all the W's are members of the lexicon. Dagger there, because there's something here to come back to eventually. The grammar consists, as I just said a minute ago, of rule 1 and the lexicon L. And the sentences of the language, those are the things generated by rule 1, consist of all strings of words in the lexicon. And of course, the corpus is one of those sentences. The corpus is in L plus, that's to say it's a sentence. The corpus C can be created by concatenating words in the lexicon. The corpus C is a sentence generated by a grammar, right? We need to compute a distribution P over the lexicon L. That distribution is going to be computed empirically. That is to say, it's going to be based on the number of occurrences of each word in the way that the corpus was divided up into words 2 steps above. We'll come back to this very important step below. But when the corpus is really a string of letters from the alphabet, and we're interested in various parses of it, breakings up of it into sequences of words. And as you can see, there's going to be more than one possible way to do that. The probability of the corpus is the product of the probabilities of each of its words. And we can calculate the plog from that. So the plog of the corpus is the sum of the plogs of the individual words. Each word W in the lexicon L contributes to the bit length of the lexicon in 2 ways. So we're computing, as I say, the length of the lexicon, and each word contributes to that length in 2 ways. There's the bit count of the individual letters in W. So if the word is the, for example, THE, then it's going to contribute, it's going to cost approximately 5, a little bit less than 5 bits for each letter. If we take the cost, the information cost of a letter to be log of 20, the base 2 log of 26, it's a little bit less than, the base 2 log of 32 is 5. So the cost of each letter is almost 5 bits. And the length of a pointer to W, we'll talk more about that, but just take my word for this at the moment. We're going to calculate the length of a pointer to a W, and that the cost of that, the number of bits of that, is the plog of the probability of W. The reason that a pointer costs that much in bits is a really central, very important fact from information theory, and we'll get back to that eventually. Okay, so now we can talk about how we're going to learn this grammar. We're going to do it in an iterative fashion. So we're going to begin with the following. It's step 1 there. I've got this table here with only the first row in it. It's step 1. It's the first row. The alphabet is A. That's fixed. We got it in advance. We're never going to change it. We've got a lexicon, and right now the lexicon is just A. That is to say, capital A, the alphabet. So if the alphabet is the letters A to Z, then the lexicon is the letters A to Z. The corpus is fixed. It's given to us in advance. The bit length of the lexicon is essentially 0. The lexicon, well, it has those 26 letters, so it's not 0, but compared to what it's going to be, it's pretty darn close. And then the plog of the corpus, well, that's going to be very large. It's going to basically be a little bit less than 5, the cost of each letter, times the number of letters there are in the corpus. And if it's 1,000,000, means that the plog of the corpus is going to be a little bit less than 5 million. And the description length of this corpus is equal to the number of bits in the grammar which is the number of bits in rule 1 plus the bit length of the lexicon, which I said was very close to 0, really, plus the plog of the corpus, which we've just seen is a little bit less than 5 million. So basically we've got numbers there. The description length of this corpus is a little bit less than 5 million. We're going to go through a process iteratively, and as we do it, the description length is going to decrease because the plog of the corpus is going to get smaller. It'll decrease, decrease, decrease until eventually it stops decreasing, and then we'll stop. Okay, so here's what we're going to do on each iteration. On each iteration, we're going to create k new members of the lexicon L. Let's say k is 25. That's what I usually do. We create candidate new members of the lexicon in the following way. Okay, on any given iteration, we know the corpus, C, can be parsed in many ways, except on the first iteration when there's only one way. So, for example, if the corpus contains the substring THE, then it can be parsed as the word THE. After a couple iterations, the is already a word there. Or it might be parsed as THE, because those are each of those letters are members of the lexicon. And it might be parsed as TH, followed by E if TH is a member of the lexicon, which it will be by iteration too. So there's multiple ways that the corpus can be parsed, and we always choose the highest probability parse. I'll call that capital P, and we ignore all the others. I'll get back to this when I say a little bit about expectation maximization, because this is a bit like expectation, but not being done in all its glory. Far from it. Okay, so that's the first step. Now we create a set of k new candidates on an iteration by considering all pairs of words in the lexicon that appear adjacent to each other in a fixed order. And so like on the first iteration, T and H will appear next to each other more than any other pair of words. T and H are words. So on the first real iteration through, T followed by H is going to be at the very top of the list of candidate words. So we rank the candidate words by the number of times they show up in the corpus, and then we pick the top k of those, and we say those are our candidate words on this iteration. So we have to assign some probabilities to these new candidate words, and we do that with counts. So these new candidate words have certain counts, which are what they are, and then all the other words in the lexicon also have counts. Those counts came from the number of times they occurred in the parts of the whole corpus on the previous iteration. So we add all those counts up. That gives us a denominator, and the numerator for each word is the number of times it occurred. That gives us probabilities. If you're following all the details that I've got here, there's a little bit of overcounting, but it doesn't matter. It's going to go away in the wash, so to speak, in just a moment. Because now we go down to point 2, we reparse the whole corpus C. We keep only the maximal probability parsing, P. So we count in P the occurrences of each word in the lexicon, L. Some may have 0 counts, including some of the new candidate words. We add up all the word counts and use that sum as the denominator so that we assign new probabilities to each word in the lexicon based on their frequencies. Those are counts in the parse P. You might think of this step as somehow the tricky one, but that's a crucial step. You will probably sort of get this better when we look at a particular example of this happening with real words in English. If you're familiar with expectation maximization, this is related to that, with the huge difference that I'm only considering one parse of the string rather than all possible parses. So what I did is similar to the expectation step, but I just took the maximum probability parse. DeMarkin's work uses the real expectation, but the reality doesn't seem to justify the additional computational complexity in my experience. I mean, I've coded it in both ways, but just using the maximum probability parse seems to do just as good a job when we're looking at natural language, or for that matter, when we're looking at DNA. And then when we calculate the new set of probabilities, that corresponds to the maximization step. Anyway, what we care about is computing the description length of the corpus with different versions of different hypotheses about what constitutes the lexicon. And how do we do that? Well, the description length is the sum of the plogs corresponding to the corpus and the length of the grammar. The plog of the corpus is equal to the sum of the plogs of each of the words in the parse P. The length of the grammar is the cost of rule 1, which we can ignore because it's shared by all analyses, the same rule, plus the length of the lexicon, which I talked about above, just above the defined in the bullet point just above section 1.2. Okay, this video is getting long enough. I'm going to bring it to a close, start the next video in which I will begin with looking at English and applying just this. You'll see what we get, and there's a lot of interesting stuff to learn, both about what it gets right and what it gets wrong. Both are very interesting. And I'll close with some additional material about some of the basic points in information theory that I've alluded to but didn't actually go into. Okay, see you soon.